Okay folks, welcome to Lecture 9, where we are going to talk about multiple lights and normal mapping, and just a small update that there were some website changes to hopefully make things nicer. So just bear in mind that modules going forward will have a little different look, but it's the same overall content. So when you're looking for the slides, they are here. The videos will be posted below as usual once they are up and running. So hopefully that's just a nice little cosmetic change for folks. So that's just a little bit on the course logistics. Let's go ahead and run into our lecture. And a little warm up today, just to give you an example of what we're going to be talking about. Two topics today. Multiple lights is the first, and the second is normal mapping. And on the right here in the warm-up is an example of a normal mapped wall. You can see it kind of looks cool, and it's got bumps to it. There's another name that goes sort of alongside learning this topic, the idea of a bump map, which is another sort of graphics technique to make flat surfaces appear bumpy and have more detail. So if you'd like to see how some of this is done, you can see a cool little demo on normal mapping these sort of this 3D figure of this horse here, in one such way combined with machine learning. So it's kind of cool, fun technique and graphics that we're going to get to look at. And it's really going to start to improve the realism of our scenes as we move forward. So last lecture we talked about, or at least in our lab, we had this sort of lights, camera, action lab where you're moving around in your scene with a light. So you implemented the Phong illumination model and combined that with our virtual camera. So we walked all the way down the sort of pipeline, again reviewing our MVP matrix and just how a model goes through this transformation to world space, to view space, gets clipped by the GL viewport, and then finally translated into our screen. So just a few logistics. Assignment 5 is going to be released very shortly, and for this assignment we're going to be adding normal mapping to our object loaders. Now for assignment 5, what I've done in the past is for folks who haven't gotten their object loaders working, or perhaps want to sort of restart, but still implement normal mapping, there is an alternative assignment or alternative way to complete assignment 5 for up to 95% of the credit, which would be sort of normal mapping a brick wall. So I'll talk a little bit more about that perhaps in office hours with folks if they have questions, but just know there'll be two different versions of assignment 5 released. The final project specs were also released, just to show you where those are on the website here. On module 8, I can change the color of this the font here, but again, we went through these last lecture again, but do take some time to look through those, decide what you'd like to work on, and then ultimately create your final project repository. Okay, in the final project, again, you have a lot of leeway for what you would like to implement. You can sort of use other tutorials if you'd like to learn a new graphics technique, new types of shaders and so on. Just make sure you cite those sources and push a little bit further than this tutorial, but you have a lot of freedom here, so do take advantage of that. And then as for today, as mentioned, we're covering what you'll be doing in the labs, adding multiple lights, and then this normal mapping technique. Okay, so with that, let's go ahead and get started. First, talking about multiple lights. Okay, so today's goal is going to be to enhance our previous scene and add multiple lights. So we have one light here, you can sort of see where it's shining, but we want to improve this to create more realistic scenes. Okay, so one such improvement we were learning about yesterday was sort of, or last module was how to implement an illumination model that relatively models what happens in the real world with different effects of lighting, the diffuse component, how light scatters, the specular, how light reflects, and ambient, the overall lighting of the scene. Okay, so today we're going to add multiple lights, and specifically they're point lights. And again, in order to improve the realism in our graphic scenes, just like in the real world, we have multiple light sources, and this helps create different atmospheres. Okay, so if you've ever been to a theme park where they have different lighting, or a theater, you notice that the lighting's much more different than, say, an office, to create different atmosphere. So here's sort of a nice example. This is from the Learn OpenGL website, where they're using 3 lights that are differently colored in each of the scenes, and based off the color of those lights, you can see already the atmosphere that's created. So this gives sort of a more deserty feel, maybe a factory here. Here's sort of the biochemical lab, or in sort of the scary horror film type of lighting here. So you can already see, just with the changing the colors of lights in the same scene, how dramatic of an effect it can have. If folks have ever worked in a theater, or as a technician or something with lighting, you certainly understand this. But we've all seen movies and so on, and know how this, or in games, how important lighting is. So I thought this was a nice illustration of that. Okay, so let's get to it with adding in multiple point lights into our scenes. And so a point light is something that has a position, and it illuminates in all directions, fading out over a distance. There's a nice discussion of this on the Learn OpenGL website, but again, it's just a light source. You can think of it like holding a light bulb in your hand, and it shines out in all directions, but only for a certain distance, right? When you turn your light on in your room, it doesn't light up, in your neighbor's room. There's a certain distance it works. And point lights, so this certain distance that lights work, we say they fade over a distance for how bright they are, how far the light rays travel. Okay, and this fading of light is something called attenuation. So the greater distance we are from an object, the less light that object should emit. Okay, and there's different ways to, again, model this attenuation for how light fades. Some folks say it just is a constant, so it's sort of a fixed brightness if you're within a certain range, almost like a very bright spotlight. There might be a linear fade over time, or quadratic, which is what's shown here. So if you're really close to the object, right on top of it, the intensity is 1, it's very bright, but then it has this sort of quadratic function here to fade the light over a distance as you become further away. And this creates a nice drop-off effect. Here's an example of lights falling off in sort of a constant form. As soon as you're, let's say this is 10 meters away or so, the lights don't shine at all, and you have these dark sidewalks or dark patches here. Okay, here's just another nice example of some point lights. On the left, you can see a moving one. That's sort of the red spotlight and the yellow. But you can see how, as they move over these objects, they brighten them up. But when they move away, these objects don't light up the light color. And then just another example of here of adding sort of different point light sources. Okay. So point light, if we want to create this in our scenes, we need to model these characteristics again. So what we're going to do in our fragment shaders is create an actual structure to represent this light and how it's going to be modeled. So we have the light's position, because we said this is a point light. It's like carrying a light bulb with you or moving around in the world. And then we need to, for each of these lights, we're going to model our same Phong illumination model, have an ambient, diffuse, and specular component tied to it. And then we want to model the attenuation, so sort of have that constant, linear or quadratic function. We can actually combine these in a way. You can play around with this in your scene, but how bright something's going to be 1 unit away, and then over a distance, we can multiply it by some linear factor or some quadratic factor. Okay, so again, where our light is, the color component, and then the mathematical model of how light fades, that attenuation feature. Okay, so when modeling our point light, the distance can be computed from our fragment shader. So we have this fragment position here that we can compute. So where our model is, the model matrix, and then the actual position, this is where an individual fragment is. So fragment positions computed in our vertex shader. This is kind of a little confusing thing, but we're going to use this information so we know where vertices actually are, and after they've been transformed and so on. So that's why we're going to record the fragment position here. Okay, and then we want to actually compute the distance. That is, we're going to have our point lights like we did in our previous lab. They're going to have some position in space where they exist, but we want to compute how far away our light is from a position. Okay, so we have that fragment position that we just computed, where our vertex is. So we can figure out that distance here, the length between where the light is in that fragment position, and then we can model our attenuation here. So this is just going to be 1.0, that's sort of the maximum intensity, and then follow this equation of a constant plus some linear value times a distance plus the quadratic fall off, if you will, or how much this attenuates. And since it's a quadratic, it's distance times distance. Okay, so again, the bigger our distance, or the further away our point light is, that's this guy, from our actual vertex, which is where our fragment position is, the less light contributes that final color. Okay, that's why we're dividing 1 divided by some number. So again, if this number here, the second part of the equation, is very big, then we should light our objects up much less than if they're, if this is very close. Okay, and then whatever this attenuation value is, we multiply that by our ambient component, diffuse, and specular to sort of increase or decrease each of these values appropriately. I'll just think of them as decreasing since we're attenuating. Okay, and that's how we fade out our point light. Okay, so here's an example, again, from the Learn OpenGL website. I think, again, I'm pasting this resource a few times. It's one of the ones in the module that will help folks learn about point lights and how they work. But this example shows nicely that light here to the right, you can see objects closer get brighter, but objects that are very far away, like this box on the left, are much harder to see because they're receiving less light from this light source. Okay, so you can see the light actually fading. Okay, but if we add another light in this corner, these objects should start to get brighter as expected. Okay, so on that point of, now that we know how to model 1 point light in our scene, we can actually start adding more lights. Okay, so just like, and how we're going to do this, or an efficient way to do this is, how we would do it in a programming language like C. If we want many types of something, an efficient way to do this is model those types as an array. Okay, so there's a few new concepts here. They were maybe touched on a little bit in the last lab in your fragment shader where you saw light and point light 0, but here we actually have point lights which we're going to send into our uniform as an array here. Okay, so we're going to set up our lights as uniforms. So in each of our shaders, we will set the light color, the position, maybe based off the camera, maybe a fixed place in the scene here, you can decide, and then set up the intensities and then our light model. Okay, and it's important to note that what we have here, how these things are named, are going to match exactly in our shader our point lights struct, so has light color, position, followed by intensity, strength, and so on, and even the index of that point light. Okay, so in our fragment shader, you will see this struct here, which has point light, and then again light color, position, intensity, and so on. So again, the member variables are going to match the uniforms we have set in our C++ code. So remember variables being these things like constant, linear, quadratic, ambient, light position, etc. And then in our C++ code, again, we were just setting up our uniform. So if we had 3 floats, that was our vec3 here, light color, which is 3 floats here. Okay. There's you can again just observe that the uniform is an array of point lights in our fragment shader. So that's this guy here, where we're setting this up. We're saying, hey, we have this uniform. Again, uniform means we can talk uniformly or between the CPU and GPU. We're passing values constantly. But this point light type here, which is declared here, and then what it's called here. So this is where it's sort of declared, or the memory exists. And there's just one light here. So you'll have to increase this for your scenes to create more atmosphere, and then set up your uniforms appropriately. Okay, so some sample code. I've included a possible solution from the Learn OpenGL site, or based off of it in the repo, but you'll need to study it and change it a little bit to actually give some atmosphere. Okay, so it's fair game to base your code off the sample provided, but I want you to learn a little bit about writing functions in GLSL. Again, sort of expanding our notion here. And remember that GLSL, the GL shading language, is just OpenGL specific, but it's a C variant language. So if you already know C and C++, like we've been doing, you know all the syntax. Use some loops, and you can have multiple lights within one shader here. Okay. So I sort of have my note, don't just copy and paste in the stuff that's given, but actually type it in, modify it, try to write some of these things as a function instead of just putting everything in main, and really play with the shader code. I think that's how you'll write better shader programs, by manipulating them and trying some things. Okay. So you can see here's a sample here, where I've added a function called calculate point light, where it takes in a point light, normal, for some object, the fragment position, and where you're viewing it from, and actually models that light and how much light is being contributed to the object's or the fragment's final color. So do take a look at this. It's kind of nice to look at the body of code and just again see how we've separated things out to functions, and really try to study this. Okay, so your goal for the lab is going to be to modify object update with uniforms. Again, so you need at least 4 point lights. You can add more if you like, and to create some atmosphere. Okay, so you're going to also have to add the attenuation equation. So where was the attenuation equation? Well, it looks like it's in this calculate point lights, so you'll have to make sure you model that and include that and understand it, and add an actual function in your GLSL code. Okay, so you'll have the sort of grass with a brick wall scene, but I've seen folks do some cool stuff where they have lights moving around, or maybe fixed lights that turn on and off at certain intervals. So do really play around with it. I think it's a fun lab. Okay, so some common gotchas with this lab that you might encounter is the screen being black. That means you likely have a light that's 0 that's getting multiplied in, so none of your lights are contributing any light to objects. So initialize all your vectors. If the screen gets too bright, turn down your ambient intensity. Try testing with just 2 point lights at first. If you have 100 lights, for example, if you go a little bit wild in a very small space, your screen's just going to get very, very bright. It's going to turn into just sort of a white image, or something otherwise very exaggerated. If you can't tell your lights are being drawn, think about your coordinate system. The positive z direction again is behind us, where our camera is looking. And start with positioning your lights somewhere nearby that's reasonable. 0, 0, -1, 1, 0, -1, etc. You can print out the positions in the console, print where your camera is, and sort of use that to debug the graphic scenes. Okay. So with that, if you haven't already, do give yourself a 5-minute break if you'd like. Okay, and if you're joining us, welcome back for part 2. And we're going to shift gears and talk a little bit about normal mapping. And this is in efforts to get you ready for your normal mapping assignment, in the sense that this is sort of the final part of our object model loaders. Okay, so our goal for the normal mapping portion is to add lots of detail to our object models without slowing down the computer. That's sort of, we're going to implement normal mapping in the vert GLSL, fragment GLSL shader, so we can show a lot of detail by utilizing textures and our GPUs to render detail as opposed to lots of triangles. Okay, so again, use these slides for helping you implement normal mapping. I'm sort of thinking of this portion of the lecture as a supplement just to help you. Again, reading through these in chronological order as you need. Again, the intent is that this will be your main resource for helping you with the assignment. This and the Learn OpenGL website. Okay. Okay, so adding detail in computer graphics, again, we've had some strategies so far where we've added textures and that started to make our scenes more realistic, and then we can always add more triangles to modify our geometry, get more detailed shapes. Okay, so again, with adding textures, I want to focus on this sort of subset of adding detail. Is that again, when we add a texture or our diffuse texture map, which is one of many that we could add, it's a way to color a triangle on a per pixel level. Okay, so because previously when we colored a triangle, we had to do it per vertex, which wasn't very detailed. By adding a texture, this was a really big step because, again, we could do things on a per pixel or per fragment level. Okay, so we have much more, usually many more fragments than vertices in our scene. So more pixels than vertices. Okay, so textures are a great way to add per pixel level detail into our fragment shaders. Okay, so if our other strategy, if we, as mentioned, try to add more triangles, this is really good, but as we add sort of infinitely many triangles, or just many more, that's a lot more information for our GPU to sort of compute. Because remember, when we add a new triangle, we're adding a whole new set of calculations that we have to do with rasterizing that triangle and determining what the winding order is, and if it's a back face, and if we should even draw it, or if it's off the scene and should clip it. So that's a lot more information we need to process. So this is an example of just a shape where we've added more detail. So this 6,000 triangle model to 6 million, and you can see there is a lot more details, right? You can see even the wrinkles on the face, and some of the higher detail here on the model. But the better approach, again, is to just add more texture detail, okay, instead of adding more triangles. And this has been the theme for the past decade or more, really, maybe even 20 years, I would say, of just how to add more detail in your scene. So adding bumpiness and depth into your models. So the question is, though, how can we do this without using more triangles, or our diffuse texture map really doesn't provide this information of depth. Okay, so the solution is to use a special texture called a normal map that extracts the detail of a high polygon model, so something like in the middle, and then can save that information as a texture and apply it to a lower polygon model. Okay, so you can see here what's pretty cool is, again, in the middle is our high resolution model, on the left is our low resolution model. We've captured this high resolution information from the middle and generated a normal map, so a texture applied to this surface that gives it a lot of detail. So you can even see stuff like the shadows. You can still capture a lot of those wrinkles here. So if I had to ask you, how many polygons this was, between the three models, you would likely say this one has a lot more than the 6,000 one. But in fact, they're the same, and it's just the something we already know how to do, which is apply a texture map to get this amount of detail. Okay. So here's another view of it, if you don't sort of believe that rendering, of taking this 4 million triangle model, applying a normal map to a 500 triangle model, of it and getting this highly detailed scene. So this is again really cool just to see that these two depictions here are nearly identical, but this one has a lot less detail. Okay. So again, and then if we're just looking at this and trying to figure out what's going on, is the topology or the geometry, it really is the same if you look at some of these triangles, but really what's happening is just on a per pixel level. Again, we're using this information to tell us as a texture how dark or light a pixel should be. And then when our eyes look at this picture, we get a sense of depth here in this image. Okay. So this is just a little aside. If you want to see how high polygon models are made, to get these incredible amounts of detail, usually you have specialized 3D tools. ZBrush, 3D Max, Blender 3D all have these sort of sculpting tools where you can model an object like clay in very high resolutions and generate these cool models like this. And this is how you get the highly detailed high polygon model, and then you can generate a normal map from it. Okay, so here's what the normal map looks like. We looked at one briefly in a previous lecture. So here's the green lantern. This model is normal map. And the idea is, again, you get this sort of bluish image, which each individual pixel is an encoding for a normal vector on a higher resolution model's surface. Okay, so where were all of the, if I go back here, the normal vectors of each of these triangles, and I've captured that information as a texture, and then it generates sort of this bluish image. And again, it's blue because, again, a pixel is made out of red, green, and blue pixels, which we encode as X, Y, and Z directions, and the blue is always 1 because the model is facing towards us when these are generated. Okay, so here's a more typical example we'll work with. This is the one you're going to work with in your assignment because it's easier to tell if it's right, or this is one path in your assignment. Actually, as mentioned, assignment 5 has 2 parts to it, so you can model the either you'll do a brick wall or you'll add to your object loader, and the brick wall will get you up to 95%. So same shader, so either way, as long as you get the shader working in assignment 5, you are good to go for at least 95% of the assignment. Okay, so again, here's the texture map, here's the normal map of the brick wall. I want to focus just on the normal map for a moment. Again, it's just the texture, so we're going to load this image data as we previously did into memory using glgen textures, and then sample from this normal map each individual pixel, which we refer to as texels. When we have a texture on the GPU, we call them texels instead of pixels. And then we'll sample each individual one as X, Y, and Z data, or normal vectors on a per pixel level. Okay. So again, the normal map made from the high polygon version 3D model with lots of triangles. Each of those triangles had a normal, and then we encoded that normal as an R, G, and B value for a vector. Okay, and there's 3D tools that sort of automatically do this for us, which is pretty cool. Okay, so at this point, let's think about what we need to do in OpenGL. We want this sort of image or something that looks like this, a bumpy brick wall, but really we know it's just 2 polygons, okay? But it looks like it has much, much more detail. It's just a diffuse texture map and a normal map. Okay, so we need to load in 2 samplers, diffuse texture map and the normal map here, okay? And then, well, the question is, we have these normals that we can sort of use, and once we have normals on a per pixel level, we can actually think about where our light sources are and how bright to make each of those pixels, okay? But when we get these normals, there's one issue here. Because what if I rotate this object? How do I update the individual normals on a per pixel level? Okay, so again, here's just another illustration of the problem, is that our normal map is generated assuming that the plane is facing the camera directly. That is, we're on a sort of front facing view of this object, and we say, okay, let's generate the normals at this particular orientation, okay? But if we tilt our object, the data in this texture is not changing, okay? It's a static image of this texture, and if we rotate our object, let's say we turn it 180 degrees so the brick wall is facing away from us, well, we haven't updated our texture, which has that normal information, right? It's changed, okay? So the normal orientation is again relative to each face, and our geometry is not changing. So we're going to solve this problem. We need to do one more step by computing what's called the tangent space to compute the lighting of our final object. Okay, so tangent space is yet another space, right? We introduce more abstraction and spaces to help us render our scenes properly. But this is, again, we're rotating our normal data by, we're going to use something called tangent space to compute our final image, okay? So remember, our normal data is a vector. In an OpenGL, we rotate vectors with matrix transformations. We rotate this or move it or whatever, okay? So we're going to multiply in some other tangent space matrix to make this work for all orientations, okay? So the twilight zone, no, I meant the tangent space. This is weird space that we're in now. Tangent space is also sometimes known as a texture space, so you can read a little bit about here. But again, just putting this into perspective, we've worked with something called object space, setting our vertices to some position to the origin. We've worked in world space, which is translating that object in our world. And then we've worked with eye space, where our camera is and views the world, our viewing matrix and how we project things. Okay, so this is just another space that we're going to work with in our vertex and fragment shaders. Okay, so let's just focus on this tangent space for now. We've talked about the others and how to compute tangent space. Okay, so how we think about this is, remember again, we've talked about texture maps also being UV maps. So sometimes we use the terms U for the x-axis and V for the y-axis, and then N for our normal pointing out. That's the blue value, I guess. So R, G, and B here. So again, our goal is just to transform a given texel, so just one of these texels here for each one in the image, to make sure that's in the same coordinate space as the object. That is, so if I rotate this object, I need to, in a sense, rotate that texture or what that normal is. Okay, because then once I've done that, this texture that we're pasting on our object is in the same space or same orientation as our objects that we rotate. And then we can use this normal map for lightening and darkening our pixels, right? We can just, on a per pixel basis, take the dot product of where our light source is and figure out how what the color should be, very bright or very dark. Okay, so how do we compute the tangent space? Well, in order to compute some space or one of these matrices, we need 3 vectors, right? This is just another 3x3 vector here. So we have their normal vector already. That's one of these texels here, a U, V, or N, or an R, G, and B value here. And then we can get a, we have then, this vector that's just pointing out here, our actual normal, so the surface normal of our figure here. And then we need a tangent, okay? So some vector that's parallel to the surface, okay? And so we have lots of those that we can choose from, just anything that's tangent to this surface normal, or rather this one in blue here. And we're going to choose the one that runs along our texture coordinates here, okay? And then one more vector, because we need 3 to make a space, okay? So to sort of orient us and give us an X, Y, and Z axis here, okay? So this little coordinate system gives us a new space. Now if I've got 2 vectors here that I've picked, so one is just our surface normal and then one that runs alongside the texture coordinates, I can always compute a 3rd vector by, pause and think about what the mathematical tool is for that. And if you've had some time to think about it and think back on the math lectures, we can get a vector that's perpendicular to two others by taking the cross product. Okay, so the cross product of our normal and our tangent vectors. Okay, so when we have all three of the vectors computed, we have a tangent by tangent normal matrix. Okay, and once you have this, you're ready to go. In the supplied code, you will see that there is a geometry CPP file where this is already being set up for you, where I've already computed at least the normals for the geometry, or as you add every triangle in our scene. Okay, so once you're comfortable that you have this TBN matrix, or the tangent by tangent normal matrix, our tangent space, you're ready to start editing the shaders. Okay, so this means you're going to need several uniforms bring in this information, and then you're going to be passing some of this information from your vertex shader into your fragment shader. Okay, so you're going to be taking in some information of where your normals are and then passing them out to your fragment shader. Okay, so just a few sort of FAQ things. So where are you computing the TBN matrix? You're doing this in the vertex.glsl, because this is where we move and orient our geometry, our brick wall that's spinning, or your object file, where you're putting all of your individual vertices. Then you use this TBN matrix to manipulate things like the light, the view position, fragment position. And I say yes if you mean, again, you're manipulating these by multiplying through the TBN matrix on things like where this normal texture should be viewed from and where its actual fragment is. And then you'll use something like tangent, after you've multiplied your fragment position by the TBN matrix, name it something nice like tangent fragment position, and that's what you'll actually be using for your lighting computation. Okay? So additionally, remember, you have your normal map that stores information, you have your diffuse map that stores information, and again, you're going to use these maps to figure out how light or dark a pixel is. The diffuse map is just a pure color, but your actual normal map is what you're using. Okay, so think about what that computation is. Again, I might have given some analogies or given that answer away already. The angle between two things, two vectors, how do we compute that? And just some sort of closing words on normal maps, the pros and cons, because we should know about this technique. They're not always perfect, but the pros are, we don't need a lot of polygons. This is a big win for us, being able to offload a lot of this work to GPUs that can render, lots of data and do sort of lots of these dot product computations, if you will, to figure out how much to light up individual pixels. Okay, artists also have control over the normal map and how much detail they need. The cons are, we still need a little bit of a memory for that texture, the extra texture, but it's not a lot in comparison to having all that geometry. And the details still, it's a little bit flat, meaning we still have a brick wall. So if you look at it totally from the side at a perpendicular angle, you will notice it's flat, but it gives a good enough effect that we like that. So if you're trying to map or sort of create a scene of like a mountain or something, a normal map's not the right tool to use because the geometry again is still not changing. Okay, for your assignment, for at least the part of it, just to show that the normal map's working. Here's just a successful implementation of it, so you can use these for reference. You'll see this sort of nice shimmering brick wall, and then you'll see from the side it shimmers a little bit less. You'll know if it's right if when the wall turns around, if the object's very dark on one side and bright on the other, okay? Because that will tell me that your normal direction is correct for the texture map, okay? Your texture map, your normal map and your object might sparkle a bit at sharp angles, and that's okay. That's the specular light sort of adjusting, and that's okay if you see a little bit of shimmering. But overall, it should look something like this, where you can start to perceive some depth in your object. Okay, so that's the end. and you know your comrades before you have made some common mistakes. So I've listed those here. You can look at these as needed, and this might give you a few hints on the assignment. Again, I'll release that very shortly. Probably by the time you watch this video, it'll be in your repository, but do take advantage of that. Okay, a few more video supplements if you want to see a little bit more on normal mapping, what it is, again, defined, in practice, what scenes look like with and without normal maps. And if you want, you can read the actual paper, Normal Mapping Simulation of Wrinkled Surfaces by Blinn, to help fully understand this technique. I think it's actually a nice read and it's not too long. Okay, thanks for watching. We'll see some of you in office hours, and I hope everyone else is otherwise staying well.